All right, some more review picking up from where we had left off. If you were using the first derivative test with critical numbers x equal -3 and x equal 1, how would you fill in the last row of this table that we see here? So first of all, remember that we got these intervals that we would use for the first derivative test, and then we chose some numbers that we would test in the derivative, and then we have tested those numbers. So f prime of -4, that equals -15. F prime of 0, that gives us 9, and then f prime of 2, that gives us -15. So of the choices that we see below, how would we fill in that last row? Here we're just using some words, increasing or decreasing. One thing we want to notice is how this relates to the first derivative test. If your first derivative is negative, then that tells you that your function f is decreasing. The slope is negative, so it is going down. On the other hand, if the first derivative is positive, then that means that your function f is increasing. So in this case, we see at -4, the first derivative is negative, so we get decreasing. And then at x equals 0, the first derivative is +9, so we get increasing. And then finally, at x equal 2, the first derivative is -15, so we get decreasing. So our answer here is C. Continuing on, if you were using the first derivative test with critical numbers x equal -3 and x equal 1, how would you summarize your critical numbers? So here we see all the information we had just discussed repeated in this table. And so what we are trying to answer with the choices here are things about relative, max, and min. And it might be helpful if you just think of some of the diagrams that I had drawn. Like if you have decreasing, it's like you have your function is going down. If you have increasing, it's like your function is going up. And if you have decreasing, again, it's like it's going down. So what that means is at the critical number -3, we get what's at the bottom of a graph that goes down and then comes back up. That would be a minimum. And then at the critical number 1, there's a maximum. So we have a relative max at 1 and a relative min at -3. And so our answer here is D. Organizing your information into a chart like this is really helpful in trying to get to these answers. All right, something else to consider with this function. If f of x is equal to 12 plus 9x minus 3x squared minus x cubed has relative minimum at x equal -3 and relative maximum at x equal 1, as we were just talking about here, how would you classify the endpoints if they were -5, 7? So meaning our domain is restricted from -5 to 7. So in this case, it might be helpful if we go back to that chart that we had here, and we can think that our endpoint over here on the left is -5, and then over here on the right is 7. And it might be helpful to think that in these intervals, we essentially have decreasing on both of them. So you can think that for -5, you're coming from a high value and then going down to the minimum. And then for the other interval, as we're heading towards 7, we are decreasing down to a low value. So you can expect that you would get a maximum at -5 and a minimum for 7. All right, so now consider the function g of x with critical points x equal 4 and x equal 13. The second derivative test produces g double prime of 4 equals 7 and g double prime of 13 equal -2. What does this mean? So remember, with the second derivative test, we plug our critical numbers into our second derivative. And if we get that our second derivative is positive, like g double prime of 4 equals 7, that tells us something. And also, if g double prime of a value is less than 0, like g of 13 equal -2, that also tells us something. And so what I would remind you of with this is how this relates to concavity. With g double prime being greater than 0, that's talking about concave up. What's at the bottom of something that's concave up? That would be a relative min. And then if your second derivative is negative, that's concave down, that would give you a relative max at that critical point. So in this case, since g double prime of 4 equals 7, that means that at the input of 4, we're getting a relative min. And then for g double prime of 13 equal -2, that means at x equal 13, we get a relative max. So our answer here is C. Now let's take a look at another answer that is here, and let's try to understand why C is the correct answer. If you look at the answer for part D, it says there's a relative minimum at 4, 7. That seems like that should be the right answer because x is equal to 4. The problem is the y coordinate for this minimum is not coming from the second derivative. Remember, your y coordinate, or the second coordinate, has to come from plugging the number into the original function itself, which we don't know what that is. So we can't find that. So that's why the answer for this is C. Okay, now a review of finding some points off of a graph. So first, list all stationary points. What I would remind you of with this is this relates to your graph essentially being stationary, not moving. It also relates to when you think of a horizontal tangent line or when you reach a max or a min. So in our case, we can see a couple of stationary points related to some max and min. And there's also another stationary point where it looks like we have a horizontal line, like right here, which would be when x is equal to 1. So as far as the 3 points that we get, we have this one is at -2, 1. Remember, it's the horizontal input, the vertical input. And then this other one, which is at -1, -2. And then the third one, which is at 1, 3. We don't consider the endpoints stationary points. Now let's compare that to singular points. If you go back to the notes from when we first started looking at this, related to the first derivative test, singular points on a graph, that's where we're looking for a sharp corner to the graph. This is the same graph we were just looking at, And there aren't any sharp corners on this. So in fact, the answer is none of the above. Okay, list all relative minimums. So they're relative, so we're just looking for any low points. We've got a low point at -4, -2. We've got another low point at -1, -2. And that's it. This stationary point up here that we were looking at before, that isn't a minimum because it's just something that's sitting horizontal for a bit and then continues on its way. So in fact, the answer here is just A. Now let's look at relative maximums. Here again, we can consider an endpoint. Even though it's not stationary, we can still consider that as a relative max. And we also have a value here. So as far as our 2 points, they would be -2, 1, and then 3, 6. So now we have absolute minimums. Remember, with absolute minimums, you want to think it's the lowest point overall. If we go back to our relative minimums, we had 2 points. Your absolute minimum would come from those points. But what I would notice is that with our relative minimums, we have the same output, -2. And that's what we're looking for when we're thinking of a max or a min, is the vertical value. So in this case, since it's the same vertical value, -2, that actually becomes the same answer for our absolute minimums because they reach the same lowest point. Neither one is lower than the other, so they are both considered absolute minimums. In the same way, if we consider absolute maximums, we should go back and consider our relative maximums. Notice here we had 2 points, but if you were to compare them, you can definitely say that one is higher than the other. And in that case, your answer would be 3, 6. This point up there.